So good evening. Today I am going to start the precipitation hardening. We studied little about the precipitation hardening in last week doubt session. So precipitation hardening sequence is the first is the isothermal heating. For a certain period. Second is quenching, and third is aging. So aging can be of two types. The room temperature or at a higher temperature. So room temperature aging will call as natural aging. And the high temperature aging will call artificial aging. So how can we recognize that one aluminum alloy is a supersaturated solid solution, natural aged, or artificial aged? So for that, one designation is used for tempering process to identify the processing of that specific alloy. Like if so there are temper designations. So temper and condition. So if one later is there for F after an alloy, F stands for as fabricated, O stands for annealed, W stands for wrought or solution heat treated. And then after that, if later T followed by a digit is shown, that is used for different aging or deforming process, shaping process. Like if there is T4, then the alloy is solution treated plus natural aged. If it is T3, then the condition will be solution treated plus cold worked, and second is and the followed by natural aging. Then if T1 is there, it will shows the quenching from an elevated temperature. Of shaping process, natural aging. Similarly, T T2 represents quenching from elevated temperature of shaping process plus cold work plus natural aging. If there is T5 represents sun quenching plus artificial aging. T6 represents for solution heat treatment plus artificial aging up to peak hardness. If there is T7, then it represents the solution heat treatment plus stabilization. Up to overaging. If there is T8, it represents solution heat treatment plus cold work plus artificial aging. If it is T9, represents solution heat treatment plus artificial aging, then cold working. T10 represents quenching from an elevated temperature shaping process, quenching plus cold worked plus artificial aging. So here we see that the T2 is quenching plus cold working plus T5 is T8 is cold work then plus artificial aging. But T10 is the quenching plus cold work plus artificial aging. Then if the T6 temper is followed by two more digit T651, it represents the stress relieving by stretching, that means stress relieving by stretching to remove the compressive residual stresses, while T652 represents the stress relieving by compression to remove tensile residual stresses. Hi Monir.
Good evening, madam.
Good evening. So can we start the class? I wrote something already.
Yes, ma'am. Yes, ma'am.
Okay. So in last class we studied the precipitation hardening little. So in that precipitation hardening, the process follows the isothermal heating, quenching, and then aging. So in aging only, aging can be done at room temperature or high temperature also. The room temperature aging is called natural aging, and the high temperature. Are you able to see the screen?
Yes, ma'am. Visible.
Okay. Then the high temperature aging is called the artificial aging. Did you attended the week 4 assignment?
Uh, Partially complete है मैडम. Yes, I have.
Okay, partially completed. Then, so how can we distinguish about different condition of the alloy? Like if it is solution, means the tetra S is represent the supersaturated solid solution. Na is for natural aging and AA is for artificial aging. So how can we recognize that one alloy is solution means saturated solution, natural aged or artificial aged? For that, temper designations are used. So if a different temper, so in the temper, different alphabets or digits are used to define the material condition. So if it is there, if f is written anywhere else, if following by the if example, if the written is like 2024 f. So the 2024 alloy F represents that it is as fabricated in condition. So the condition of this F is as fabricated. Uh, Similarly for O, it is the condition is annealed. For W later, it is solution heat treated. If the temper, if T is followed by digit, and then it mean the other treatment also with the solution treatment. So T4 represents the solution treatment with natural aging. T3 represents the solution treatment plus cold working plus natural aging. T1 T1 shows the quenching from elevated temperature of shaping process plus natural aging. T2 represents the quenching plus cold work plus natural aged. The T5 represents the same quenching from elevated temperature of shaping process plus artificial aging. Then T6 represents the solution heat treatment plus artificial aging till peak hardness. T7 represents the solution heat treatment plus stabilization process, means the overaging. The T8 temper designates the solution heat treatment plus cold working plus artificial aging. T9 represents for solution treatment. First is artificial aging and the second is cold working. So the T8 and T9 are the reverse of the process. Means in T8 first is cold working, while in T9 first is artificial aging, then followed by cold working. In the T10 condition, the quenching from an elevated temperature of a shaping process, followed by cold working, then artificial aging. And if the T6 temper is followed by two more digits like 5-1, that is the stress relieving by stretching to remove the compressive stresses. The compressive stresses are stored in the material as residual stresses. So the T651 is used to remove the residual stress from the alloy. Then the T652 represents the stress relieving by compression to remove the tensile residual stress. So T651 is used to remove compressive residual stress, and T652 is used for removing the tensile residual stress. So do you have any particular doubt, or I can continue?
Continue, madam. One more doubt था.
Yeah.
टेम्परिंग एंड एजिंग दोनों में डिफरेंस क्या है?
टेम्परिंग एजिंग के बाद होती है, फिर एजिंग इज डन फर्स्ट,
ओके.
देन टेम्पर कम्स.
ओके मैडम.
in the process of aging, tempering, and the stress relieving operation, the time and temperature also plays a role in defining the precipitation and the precipitate size. Means precipitation behavior and precipitate size. So the time temperature, we can relate it to the kinetics of the reaction or process. Like if we check if the aging or tempering is done at lower and high temperature, let's say 120 degree Celsius. So the if we see the time that at lower temperature or room temperature, it will take much time as compared to the high temperature aging or tempering process. At high temperature the kinetics will be high, while at low temperature the kinetics will be low, so it will take more time. So at 120 degree it will take only few hours for precipitation. So we will study now the natural aging. So in natural aging means the alloy the alloy is quenched from the solutionized temperature, so it is called supersaturated solid solution. So if it is kept for a few days or few hours, then it will called aging. So due to aging, the excess solute atoms will squeeze out from the saturated solid solution and form cluster. So excess solute atoms form cluster at a definite plane or certain planes. So can you explain why only certain planes the excess solute atom cluster?
No idea, madam.
No. Okay. So why only certain planes? Because the different planes have different interfacial energy. So if a plane has a low interfacial energy, then it will be easy to cluster at that plane, or precipitate formation on that plane will be easy as compared to other plane which has the higher interfacial energy. That's why only certain planes which has low interfacial energy are preferred for precipitation by the solute atoms. So the solute atom cluster to form the GP zones. Cluster of atoms up to few atomic distance. Thick. So why it is called GP zone? Because the scientist uh, Gina Preston uh, discovered this phenomena of precipitation hardening. That's why the this precipitation process will in precipitation process the cluster of atoms and the uh, precipitate are named as the GP zones. So initial cluster are named as the GP zone 1, then GP1 or GP2. So how the cluster of atoms in initial cluster of atoms in contribute in increasing the hardness of the alloy. So the GPs GP zones have mismatch with the matrix. Matrix is the aluminium alloy. Means you take the aluminium matrix or aluminium copper or say for the 2000 series. So the GP zones have mismatch boundary with the matrix. So that mismatch create the lattice strain in the around the matrix. That lattice strain will hamper the dislocation motion. So if the dislocation motion is hampered, then more stress will need to apply for further deformation, and the strength is higher. So and the strengthening happens. Lattice strain results in strengthening. And now we will discuss about the artificial aging. So if we plot a diagram for the hardness versus time, the general curve is looks like this. So at the starting of the curve, GP zones are formed. The curve starts from here because the alloy has certain hardness in the supersaturated solid solution condition. So first, with initiation of the clustering of atom, GP1 zone are formed. That followed by, so with it, as the GP zone forms, the hardness increase with the so the hardness increase as the more atoms attached to that cluster, means the thickness of the cluster is increasing. So after some thickness, theta prime is formed. The theta prime is also called as the GP2 zone, which has higher thickness as compared to the GP1. Next, precipitate will form as the theta prime, that has the maximum hardness of the alloy. Means up to this time, if we age the alloy up to this time at a certain temperature, then peak hardness will be achieved. Then after the peak hardness, means the precipitation for precipitate form at this position. After this, the coarsening of precipitate starts. So the coarsened precipitate decreases the hardness of the material, and the final precipitate is called the theta, that is CuAl2 for the aluminium copper system. So for the precipitation hardening also happens in the aluminum magnesium silicon, that is 6000 series and 7000 series also. So we will study further the different precipitates in the 6000 and 7000 series also. So what is the sequence of the precipitation hardening? So first is the supersaturated solid solution that will age to form the GP1 zone, then GP2 or theta double prime, that is followed by theta prime, and then theta at the overaging. So after the peak hardness, the aging process is called the overaging because it leads to the coarsening of the precipitate. So in the artificial aging, different types of strengthening mechanism work to increase the hardness or strength of the alloy during the precipitation hardening. So similarly with the natural aging process, artificial aging also has the lattice mismatch of precipitate with the aluminum matrix. So that this lattice mismatch increase with time. Like if we see as the theta double prime GP zones and theta prime so theta double prime is the means the theta double prime and theta prime are coherent with the matrix, so they produce the lattice mismatch. But the theta precipitate, which is also called as the equilibrium phase, is the incoherent with the matrix. So that results in the more lattice mismatch and increases the energy of the material or reduces the residual stresses also. So that's why the theta prime is not preferred in most of the cases. Only the theta prime which achieved at the peak hardness is preferred. So first is the coherency strengthening. So in the lecture you taught about the different equations with associated with different strengthening mechanism in aging process. So the increase in strength due to coherency is written as the 6g r by b power 1 by 2 f power 1 half square, and the epsilon is 3 by 2. Here g is the shear modulus of the alloy, r is the precipitate radius or particle size, b is the Berger vector of the dislocation, f is the volume fraction of the particles, and epsilon is the strain. Second is the stacking fault energy.
Madam, here R by B raised to
Yeah, sorry,
uh,
raised to
R
1
by
by 2.
okay, madam.
It's
And
1 by 2.
B is Berger.
Yeah, b is Berger's vector.
Okay, ma'am.
So next is stacking fault strengthening energy. जो strengthening due to stacking fault energy. So the stacking fault energy in the precipitate particles and the matrix is different, because the composition is different of the precipitate and the matrix. So the stacking fault energy of precipitate will also differ from the matrix. So due to the difference in stacking fault energy, the increase in stress or strength of the alloy is written as the C gamma M just wait gamma M minus, no, this is not gamma M, this is radius, means radius of the matrix particle and radius of the precipitate divided by B, that is multiplied by rho k alpha ln of the nu m by nu p divided by E and F1 into fraction of 2 by 3. So here the C is a constant. K alpha represents the product of force separating two partials and the distance between them. Like K alpha can be seen as the force that separates the two partial dislocations in the stacking fault and the distance between those stacking fault partials. So K alpha is this. F1 is the one complex function. Small f is the volume fraction of precipitate particle. And the gamma m and gamma p are the stacking fault energy of the matrix and particle. Next is the ordered structures hardening. So in previous lectures we studied about the solid solution strengthening, in which we also studied the ordered structure strengthening. So in the precipitation hardening also the ordered structure of in precipitate exists. Like if a precipitate has some ordered structure, that is also called as the superlattice. In this case it will be in the precipitate particle. So as the interaction between dislocation and the precipitate particle, the antiphase boundary is formed. Antiphase boundary also formed during the solid solution strengthening, and it also formed during the precipitate and dislocation interaction. So due to the formation of antiphase boundary, the boundary, the energy associated with this antiphase boundary results in increase in the strength of the alloy. So formula for this is the delta sigma is equals to 2 by square root of pi e. Here E is the Young's modulus. Followed by the gamma APB divided by B power 3 by 2 R power half or F power half. So gamma APB is the energy of the antiphase boundary. One correction is there. So here it is gamma, which is energy. So in the previous cases also, these are the here mu m is the volume fraction of matrix and the particle. Here gamma, it is not R, it is gamma. So the energy stacking fault energy of matrix and stacking fault energy of particle divided by Berger vector. So means it is the energy per unit length. Here also it is gamma, means the coherency strain energy. Next is the modulus effect, means modulus hardening. So Mohan, are you attending the first time this dart clearing session? Mohan, can you hear me? Or we will continue with the lecture. So the modulus hardening, the modulus of the precipitate is different from the aluminum matrix, because it has the some atomic structure sequence like aluminum and copper. So the bonding in the precipitate is different as compared to the aluminum matrix. So the modulus will be different of the precipitate. So the local modulus change in precipitate will also increase the strength of the alloy. So the increase in strength is given as the delta G by 2 pi square 3 delta G GB power 1 by 2 multiplied by 0.8 minus 0.143 R by B or gamma by B, and in the after the bracket, sorry, So it is gamma and it is R. Sorry, R 1 by 2 and F 1 by 2. So here delta G is the change in the modulus divided by this change in modulus divided by GB, and this part of the equation is the energy term, and outside of this bracket this is radius of the particle, means square root of the radius of particle, and F is the volume fraction of the particle precipitate. So next is the interfacial energy hardening. So the interfacial energy hardening occur due to the interaction between precipitate and moving dislocation. So if one dislocation comes in front of a precipitate, it will cut through the precipitate if the precipitate particle is smaller than the certain size. So it will cut through the dislocation will cut through the precipitate, and the sheared particle will form. So in the sheared particle, the extra strip formed results in the increase of interfacial energy in the of the precipitate, means the step increase the surface in area, so increases the interfacial energy. So this increase in interfacial energy must be applied as applied stress. So the increase in applied stress due to increase in interfacial energy is given as 2 square root of sigma divided pi gamma s F by R. So here gamma s is the interfacial energy of the precipitate, F is the volume fraction, and R is the particle size, particle radius. Next comes the lattice friction stress in the alloy. Lattice friction stress are required to move the dislocation through the lattice. Means during the dislocation motion, the dislocation also feel the lattice friction. That lattice friction is called as the lattice friction stress. So the increase in stress due to this lattice friction is given as the 5.2 F power 1 by 3 R power 1 by 2 divided G power 1 by 2, and it is B square, and the sigma P minus sigma M. So here sigma P is the friction stress in the particle, means precipitate friction stress. While sigma M is the matrix friction stress. So these are the 6 types of hardening effect in the precipitation hardening and strengthening. So next so as the theta prime changes from the theta, I explained that it will form from the coherent to incoherent, means coherency is lost in the theta, and the theta is the equilibrium phase. So as the size of precipitate particle increases, the hardness decreases. So we will study the effect of the size of the precipitate. So in some time. So first we will see as the dislocation movement through two precipitate particles. Like if there are two precipitate particles and dislocation line is moving towards the precipitates. So if it is first the interparticle distance first is the lambda. So first the dislocation will bend at the precipitate particles, like is this type. Then it will go like this. Then after that the dislocation move from the precipitates, and it will form the dislocation loop around the precipitate as it moves from the precipitate. Then after this point dislocation line will straight out due to line tension, and the dislocation loop precipitates remain behind. So in this case the distance between two particles is less, that's why the dislocation motion is hampered this much. But if the particle size increase, the distance between a particle also increases. So the distance between particle increases with coarsening of the precipitates. So that will results in so due to the increase in interparticle distance, the dislocation can easily go through the precipitate. If one dislocation lines come, then it can easily pass through, and there will be no strengthening because here no hindrance to the dislocation happens because of the coarsening of the particles and increase in the interparticle distance. So low resistance to dislocation that lead to the decrease in applied stress, means the hardness will decrease. So in the first case, the stress required to bend the dislocation is given as tau equals to GB by 2R. So R is the curvature of the dislocation, D is Berger vector, G is shear modulus. So generally lambda, the interparticle distance, is referred as the 2R. So the stress can be written as the GB by lambda. So lambda tau is inversely proportional to lambda. So as lambda increases, stress to bend the dislocation decreases, and the strengthening will be low as the interparticle distance is high. So as the lambda increases, tau decreases. So this phenomena is called as the Orowan coarsening.
Madam, one question. It is inversely proportional to the particle metric surface energy.
Particle matrix surface energy. Yeah, no, it is directly proportional to the particle matrix surface energy, because as the surface energy increases, the stress required to move the dislocation will increase. So the
Uh, and also particle size directly affected or not?
no, then
If we increase the
okay,
particle size
okay.
or decrease the particle
Yeah,
size.
yeah, yeah, yeah. I will give the answer. So as the particle size increases, the surface area also decreases. Interfacial surface area, because as we see that if we go uh, below this up to the nanometer level, from millimeter to nanometer, we also see that the at the nano level the surface area increases. So if we go reverse from the nanometer to millimeter, the surface area will reduce. So the energy, surface energy will also be lower with increase in particle size.
Okay, madam.
Okay. So the with increase in particle size, the interfacial energy is lowered. So next we will see in the different types of aluminum alloys, like in the 2000 series, which is aluminum copper alloy. The sequence of precipitation and aging follows the path as the supersaturated solid solution, then GP1 zone forms, followed by GP2 zone, then theta double prime. No, theta double prime is the GT2 only. Then theta prime, then theta. So theta is the CuAl2 intermetallic. So as we studied that the GP zone is the cluster of uh, few copper atoms. So first, uh, from the supersaturated solid solution, copper atoms will start to cluster out of the solid solution. So first is the copper atom cluster. Then with time, uh, aluminum atoms add to the cluster. First, in the cluster forms of the copper atoms. So in the GP zones, the copper atom cluster is of the few atomic distance thick. Then after that copper atom cluster, these clusters are surrounded by aluminum atoms and vacancies. So vacancy plays a role in the formation of precipitate, because due to the presence of vacancies, diffusion rate will be high. So cluster formation will be easier. Means the nucleation of cluster will be easy. Presence of vacancies. So these clusters are surrounded by vacancies in aluminum atoms that will result in the course in the further formation of different this that will follow the this path, means theta prime double prime form, theta prime and theta. So this process happens due to the diffusion between the aluminum atoms, copper atoms and vacancies. with aging, the thickness of the cluster increases and reaches a constant size. So at room temperature, the thickness is around 3 to 7 nanometer, but at 100 degrees Celsius, the thickness of the cluster will be 10 to 15 nanometer. So what will be there if we increase the copper concentration in the alloy? If copper concentration is high, then what will happen, means what copper concentration effect is there on the formation of clusters or not? So as the copper content is high, it does not affect the size of the GP zones but affects their number. Means the size will not affect from the copper content, but if copper concentration is high in the alloy, the number of clusters will be high, because more copper clusters can form at throughout the melt, throughout the solid solution. So if we see that the aluminium 4 copper alloy, the number of GP zones are 10 raised to power 14 to 10 raised to power 15 per millimeter cube, and spacing between them will be 2 to 4 nanometer at room temperature. So this is for the GP1 zone. For the GP2, which is theta double prime, the shape changes from the cluster to disc shape, and that are also larger than the GP1 zones, means they are disc shape. One more thing, like in aluminum copper alloy, the plane of nucleation of clusters is the 100 plane. Means the 100 plane is preferable for clustering of copper atoms in aluminum copper system. So the theta prime precipitate are the disc shape, and the dia of these clusters are 30 nanometer. And the thickness is 10 atomic planes. Which is 4 nanometer. The crystal structure of theta double prime is tetragonal, with lattice parameter of 4.05 angstrom and 0.77 nanometer. So the theta prime forms because of the alternate layers of aluminium and copper atoms on 100 plane. It forms on the 100 planes, but it will form as the copper aluminium atomic layers on 100 plane. Next is the theta prime precipitate, which is, so theta double prime is the disc shape, theta prime will be plate shape, and the size of theta prime depends on the aging temperature and time. If the temperature and time is increased, the size of the theta prime will also be larger. So the theta prime size is the 10 to 600 nanometer in dia, and thickness is 10 to 15 nanometer. Next is the theta precipitate, which is equilibrium phase. CuAl2. So that is the shape of theta. Theta is also tetragonal, but it is incoherent. The theta prime is coherent, but theta is incoherent. So as we see in the aluminium alloy 2024, which has the composition of aluminium, 4.4 copper, 1.5 magnesium, and 0.8 manganese. So as the magnesium is also added in this alloy, it will play a role in the nucleation of precipitate also. So because of the presence of magnesium atoms, the cluster of copper and magnesium will form first. Then aluminium atoms join. So the sequence of precipitation hardening is the supersaturated solid solution, followed by GP zones, then S prime precipitate, which has the composition of Al2CuMg, followed by equilibrium phase S, which has the same composition. In the second alloy, Al2124, means in the 2124 alloy, iron and silicon are minimized to a lower level to maintain the fracture toughness of the alloy. So the 2124 alloy is used in the T8 condition, which is solution treated plus cold work plus artificial aging. So the cold work here is given to ensure enough number of nucleation sites for S prime to form. Means the cold work results in the increase in dislocation density and grain boundaries. Due to the increase in dislocation density and grain boundaries, the nucleation of the S prime precipitate will be higher if, after cold working. So the results, so the cold working is given to ensure the enough number of nucleation of the S prime to form. And here the dislocation generated during the cold working and grain boundaries act as heterogeneous nucleation sites. The 0.2% proof stress of T8 condition is 415 MPa, and it is mostly used in aircraft parts, manufacturing of aircraft parts. The 2124 alloy is also used in the T3 temper condition, which is solution treatment plus cold working plus natural aging. So T8 is the artificial aging, T3 is the natural aging. So this has the yield strength of 350 MPa, and in the T4 condition yield strength will be 290 MPa. So next is the precipitation hardening in 6000 series alloy. Which is aluminium, magnesium and silicon. So the sequence of precipitation hardening in the 6000 series alloy is the first is a supersaturated solid solution. Next is GP zones. GP zones are the cluster of magnesium and silicon atoms. Then beta prime phase will form, which has the composition of Mg2Si. Next, followed by the beta, which is equilibrium phase, has the same composition of Mg2Si. So the GP zones in 6000 series alloy are first the spherical in beginning, then elongate with aging in 100 direction. Means first are the spherical, then elongate along 100 direction. Keep in mind that for aluminum copper alloy, the formation is preferable on 100 plane. So plane is defined as the small bracket and the pointed bracket are for the direction. So for 6000 series alloy, the precipitate elongate along the 100 direction. And then later becomes as needle shape. one thing is there, as the magnesium and silicon atom clusters mismatch is lower than aluminum copper system. Means the effect of the mismatch due to magnesium and silicon atom is less as compared to aluminum copper system. So if we see talk about the coherency, like beta prime is the semi coherent. Means GP zones are coherent, beta prime is semi coherent, and beta will be equilibrium phase, which is incoherent. So beta prime is the rod shape, and beta are the plate shape. So now we know as the precipitation sequence follows the path as the supersaturated solution. Then first GP zones are formed, then precipitates are formed, precipitate particles are formed, then equilibrium phase are formed. So the 6000 series alloy, this route follows as the GP, then beta prime and beta. This at the temperature of 170 to 220 degrees Celsius. And the GP zone solvers line start from the 226 degrees Celsius in the phase diagram. The ratio between Mg to Si in the precipitate is 1.73 to 1. So silicon concentration is kept limited to maintain the high strength, to maintain the corrosion resistance of the alloy. As the silicon content increase in the alloy, it will increase the strength, but at the same time lower the corrosion resistance. So that's why lower content of silicon is preferred. So we see as the aluminium alloy 6061, which has the composition of aluminium, 1 magnesium, 0.6 silicon, and 0.25 chromium. So chromium is added to refine the grain size, means it inhibit the grain growth. So the yield strength of 6061 alloy is 275 ampere, used in architectural application for its good surface finish and good machinability. And it can, the 6000 series alloy are extrudable. So the extrudability of the 6061 is also high. Next is in the 6000 series alloy, lead and bismuth are added in a small amount to improve the machinability further. It has the low quench sensitivity that is useful in quenching from high temperature of this alloy. Means the quenching from the high temperature will result in no residual stresses and no cracking in this 6000 series alloy. The another alloy which is 6262, that is used in T9 condition, which is a solution treated plus artificial aged plus cold worked. So the yield strength of this alloy is 380 MPa. Then some other alloy are 6061, 6063 has the bright surface finish, and different colors can also be generated by anodizing. So anodizing is a surface treatment process. Next is the 7000 series alloy, means aluminium alloy 7000 series, which is aluminium zinc system. So the aluminium zinc system, the some amount of magnesium is also present in the alloy. So the ratio between zinc and magnesium is kept 5:2 to 7:1, and the precipitation sequence follows the supersaturated solution, then GP zone, then neta prime, then neta, which has the composition of Mg2Zn. In the 7000 series alloy also, first the GP zones are formed spherical, means zinc atom clusters, atoms cluster, then the magnesium atoms join the zinc atom cluster. So the formation of these precipitates are favorable on the 111 plane. So in the aluminum copper alloy it was 100 plane, and in the 7000 series alloy it is 111 plane. So with after spherical it will form as the plate shape. With increase in aging, then equilibrium phase. So plate shape is of neta prime, and neta prime after that neta equilibrium phase form, which has the crystal structure of hexagonal. So the 7000 series alloy gain the highest strength at only copper concentration greater than 1%. So the copper concentration should always be higher than 1%. Because up to the 1% the copper remains in the solid solution. After 1% it will precipitate out from the solid solution, and the increase in copper content also increases the solver's temperature. Means what is the effect of solver's temperature increase? So as the solver's temperature is high, means precipitate can nucleate at higher temperature also, means that the nucleation will start at higher temperature. as compared to the previous case where solver's temperature is low. If solver's temperature is high, then nucleation at high temperature. If it is low, then nucleation will start at low temperature. So the copper concentration helps in imparting the good stress corrosion resistance of the 7000 series alloy. So copper imparts the good stress corrosion resistance. So in the 7000 series alloy, the GP zone formation is necessary for neta prime precipitation at 115 to 130 degrees Celsius range, temperature range. Like if we see the aluminium alloy of 7075, that has the composition of aluminium 5.6% zinc, 2.5 magnesium, 1.6 copper and 0.23 chromium. So it attains the peak hardness at T6 temper condition. T6 edge means so aging at 120 degrees Celsius for 24 hours. Peak hardness. So in the 7000 series alloy, quenching rate also influences the formation of neta prime and neta precipitate. If quenching rate is low, then neta prime and neta will form directly without the formation of GP zone, and the neta prime and neta will form at the grain boundaries and dislocations. During the slow quenching rate, due to the slow quenching rate, at the slow quenching rate, the number of vacancies will also be low. Less. So that's why GP zone will form homogeneously at lower temperature, such as 100 degrees Celsius. GP zones form. So in the 7000 series alloy, the precipitation happens in two stages. First is the GP zone formation. Then for precipitation of neta prime and neta, temperature is increased. For the precipitate to form. Means aging at 120 degrees Celsius for 1 hour, and then plus aging at 160 to 175 degrees Celsius. So first the GP zones were aging was done at 120 degrees Celsius to form the GP zones. Then from those GP zones, the aging temperature was increased to 160 to 175 degrees Celsius to form the neta prime and neta precipitates. So this is all. So do you have any doubt in the today's session?
मैडम एक डाउट है,
हाँ.
कैन वी यूज T5 टेम्पर कंडीशन इन 6000 सीरीज और नॉट?
Yeah, we can use T5 condition, means T5 is what? T5 is the quenching at quenching from the higher temperature plus artificial aging. We can use T5 also because it has the low quench sensitivity na. So
यस मैम.
T5 condition can be used.
ओके.
Okay.
एंड अनदर डाउट था,
Yeah.
टू for precipitates to form in alloy,
Yeah.
in which क्या solute atom should have some solubility
Yeah.
in parent metal at room temperature?
Yeah, means the solubility will differ from high temperature to low temperature. Means at high temperature solubility is high, but we quench from the high temperature to maintain the solute concentration. That's why the supersaturated solute solution form, and as the that supersaturated solute solution are kept for long time, or that is called aging. So if it is aged, then the solute atom, extra solute atom will precipitate out because of the lower solubility at low temperature.
Okay, madam.
Okay. And yeah, we can discuss the assignment questions also. So can you see the next page which has the questions? Oh wait, just I will share the another page. So are you able to see the screen?
Yes, ma'am.
So Mohan, are you attending first time this session?
Yeah, yes, ma'am. Yes, ma'am.
So do you have any doubt?
Yeah, no, madam.
Okay. So can we continue with these questions?
Yes, ma'am.
Okay. So first is question is that for precipitates to form in an alloy, uh, the correct answer will be, guess. I mean, I am asking answer to you, Monir and
Option A, madam.
okay. No. Sorry. Solute atom should. Just wait. For precipitates to form in an alloy. Just now I explained the reason. Go through the options, then answer.
The solute atoms should have limited solubility in the parent metal at room temperature.
And one more thing.
Sorry?
One more answer. The correct answer is D. Solubility of solute
D.
atom should increase with increasing temperature.
Okay, okay.
Next is the increase in strength due to coherency strain of precipitates and matrix will be related to volume fraction as
F of minus 1 by 2.
no.
Option 4.
No, wrong.
No. Option 3.
3, yeah. It is directly proportional to square root of volume fraction of particles. The next question is, what does T4 temper in aluminum alloys refers to? The T4 temper.
Solution treatment plus cold working plus artificial aging.
No, no. The correct
Mm,
option is first. Sorry.
Natural aging.
Solution treatment plus natural aging. Next question is, in which of the following case of quenching medium precipitates are much finer if the alloy is subjected to same solutionizing and aging temperature? So the precipitates will be finer in which case? Air cooling, forced air cooling, water quenching or oil quenching?
Think the water quenching, sudden cooling.
Yeah, means the cooling rate will be high in water quenching.
Yes.
Next is, the strength and hardness of the aluminum alloys decreases during overaging heat treatment because of?
Um, Option 3.
Yeah,
Portioning of precipitates.
yeah, correct. Next question is, what precipitates shear out when precipitates shear out by dislocation, then strengthening due to an increase in surface energies?
Inversely, the volume fraction of the precipitants.
No, just now you answered the previous question. It is directly proportional to volume fraction.
Yes, sorry. Directly proportional to volume fraction of the
And
participants.
one more answer is correct in the question.
Which one, ma'am?
One, it is multiple select question, so choose one more option.
So, directly proportional to the particle matrix surface increase.
Energy, yeah. As surface energy increase, the strengthening also increase.
Yeah.
Next question is, when the aluminum alloy aged beyond the peak sorry, aging time, then
Strength and hardness of the alloy increase, but ductile decreases.
nahi. When aluminum alloy aged beyond the peak aging time, what is peak aging time? Hardness
Say,
will be low or high?
sorry, ma'am.
At peak aging, hardness and strength will be low or high?
It's low.
Peak aging time, no. First you tell what is peak aging, why we do peak aging.
So, more temperature and time, more time, ma'am.
No, no, no. Peak aging refers to the peak hardness. Peak hardness is the maximum hardness.
Max. Oh, peak is
So
max. Hardness increases.
if we age the aluminum alloy beyond the peak aging time, what will happen?
I think ductility increases. Strength and hardness of alloy decreases.
Yeah.
Sorry, my
Okay. And then
strength and hardness
okay.
decreases, but
And one more option is correct.
um, interparticle spacing decreases, ma'am.
No, no, it will not decrease. What will happen after peak aging time?
Hardness increase means if
No,
the
no.
atom particle
Hardness is decreased.
Hardness is decreased because of. So, what is the reason in decreasing
then
hardness?
space particle increases.
Sorry.
Interparticle spacing increases.
Yeah, correct. Means coarsening happens of the precipitate portion at higher aging time. Next question is, when dislocation moves through the ordered precipitate, then strengthening will occur mainly due to the formation of.
401 looping.
No, in ordered precipitate, it says. In ordered precipitate, what happens?
Staking fault.
No. In ordered phase, we also studied in the solid solution strengthening that antiphase boundary are formed in ordered phase.
Oh,
Orwan looping happens in the interaction between dislocation and precipitate. So it is correct. Incorrect, and the correct option is antiphase boundary. Always remember that the order precipitate or order phase will consist the antiphase boundary after any deformation process. So next question is, which of the following is the correct precipitation sequence for aluminum copper alloy when subjected to artificial aging?
second option, madam.
Second option.
Yeah, correct. Next question is, what does the T652 temper in aluminum alloys refer to?
Solid treatment plus artificial aging plus stress relieving by compression.
Yeah. And if what if it is T651?
Then by stretching,
Okay.
stress relieving by stretching.
Yeah, correct. So the today's session content is completed. So can we end the? Do you have any doubt, or we can end the session?
No, madam. Thank you.
Okay. Thank you.
Thank you.